Here we go. Object categories have been a primary target for ventral stream representation, and deep convolutional neural networks trained to categorize objects do learn features with a pretty good emergent match to visual system tuning. But we don't learn with millions of category labels, suggesting we could abandon the idea of category level supervision. But what's the representational alternative? One idea is to try and learn features that make each image or view of the world different from every other image. So this is instance level discrimination. What Woodall did is take each image, pass it through a deep net, but instead embed it in a 128-dimensional latent space, where the idea is to try and make each image as different from every other image. To do this, they had an indexed memory bank that stored all these latent representations. And to train it, they tried to do 1.2 million way classification. How do you make it so that each image stands out from among all the others in ImageNet? And the cool thing is that the latent space end up learning emergent categorical structure. Cheetahs end up mapping to similar points in the latent space as other cheetahs. But this indexed memory bank is a little bit like a supervised label now at the index level or image level. So we wanted to get away from this. So we developed instance prototype contrastive learning, or IPCL, and here's how it works. You take an image and now you sample from it. Here we did standard computer vision augmentations, but you can almost think of these as like eye movements over a current view. Pass these through a deep convolutional neural network and embed them in a 128-dimensional latent space. Now, how do we learn good structure here? We're going to use contrastive learning. So we're going to take each sample and try and move it towards the center, the average over augmentations. That's the instance prototype. And we're trying to move it away from the items that have been experienced in recent memory, implemented with a lightweight memory queue of the past few thousand items. And interestingly, this latent space also showed emergent categorization capacity as good as WooSnet. So now we can ask, do these learned representational spaces also show emergent brain-like fits? Maybe even better. So to explore this idea, we trained a slew of deep net models varying the architecture and the dimensionality of the latent space, as well as the learning framework. In particular, for our IPCL network, we had to use an AlexNet that had group norm layers to get it to train, and that ends up being important. We also trained the resource matched category supervised models. And since then, 2 new models have come out that also use instance level contrastive learning, but a slightly different learning rule. And we tested the representations learned in these models as well. Our brain data set is an fMRI data set you can learn more about from Kat Magri's talk. It has highly reliable responses to individual images, 72 of them depicting inanimate objects. To analyze these data, we divided the brain into 3 different sectors: early V, posterior OTC, and anterior OTC. And we did representational similarity analysis. So here's a bunch of layer-wise correlation plots on the here's the noise ceiling. On the x-axis is the model layer. On the y-axis is the correlation. Each subplot, these are different variations of the IPCL model, and the supervised line is in dark. You can see 4 different model families. Here is all models we trained, sort of looking only at the peak layer. Each gray dot is a model trained, and these are grouped by learning framework and architecture. So there's a lot in these data, and I'm going to highlight a few patterns. First is the self-supervised models generally show comparable or higher correlation with brain RDN. So you can see that with the colored bars over the supervised dark bars. And in general, it's the IPCL or WooSnet trained AlexNet with group norm layers that generally shows the best emergent match across the board. There are some exceptions here, though. For instance, the CoreNet supervised model in the anterior OTC shows a better fit than the self-supervised counterpart. The second thing is that architecture by far is the biggest factor that affects brain-like representation, more than the learning framework, whether it's IPCL or WooSnet or even category supervised versus not. Architecture dominates. The latent dimensionality didn't matter at all. So these are 3 different lines are the 3 different sizes of the latent space, not a big factor, and even emergent categorization accuracy, which I'll show you on the next slide. In fact, within architecture, the thing that really mattered the most was these internal layer normalizations, group norm versus batch norm. This really is what seemed to have a substantial impact on emergent brain-like representation. You can see that difference, for instance, there. Okay, so to compare with object categorization accuracy, here are 3 different subplots showing emergent categorization accuracy by the max correlation of any particular, of the max layer of each model. All the colored dots are self-supervised models. All the open dots are supervised models. And there's a few things to note. The first is that this little cluster is sort of the AlexNet family that aren't so accurate, but show the best emergent brain-like representation. And these new models are really interesting because this is SimCLR and MoCo. They've really improved in emergent object categorization accuracy, but that hasn't closed the gap and led to more brain-like representation. So there's still a lot of representational room to grow. But taken together, what we've shown is that there's evidence or support for a new representational goal that is instance level discrimination, where the benefit of this is you don't need to presuppose categories in advance. It operates similarly over all kinds of inputs. And here we've shown that this kind of representational goal can learn features that are equal or more brain-like than category supervised representations given the right architecture. And what this suggests broadly is that category information may be an emergent property rather than a driving force of object representation in the ventral visual stream. Thanks.